Okay, I'm Ariel Waissbein, this is Damian Saura, and this is a joint research project with Ariel Futoransky. We're going to present a timing attack against database engines, and let me start. Now, database engines are used daily to store huge amounts of data and to access this data efficiently. Web applications use them, and they typically store credit card information, personal data, security numbers, a lot of sensitive information that must be guarded. So this is why attackers target a database and the data they hold. Now, there's been several attacks against databases to compromise the data. For example, typically, an attacker can break into the web server and steal the data. This can be due to insecure configuration, lack of patching, or any problem in the server hosting the database. Also, web applications that use databases in the back end typically have SQL injection vulnerabilities and other vulnerabilities which can be compromised, and attackers can use these vulnerabilities to steal the data. Yet further, some databases that can be reached by users, but these users aren't authenticated, are vulnerable to authentication problems, and an attacker can impersonate a standard user and steal the data, or simply an authenticated user can steal all the data from the database when he's not supposed to do this. So these are all attacks from the past, and we're introducing a new attack where an attacker that is able to make inserts into the tables, but not select operation or steal or access the data, can eventually access the data and steal all the information in the database. So all this talk is going to be about how to do that. Now, let me summarize the main result before I continue with the talk. Consider a populated database with a lot of data. It has many tables, and one of these tables has a sensitive information in one of the columns. And an attacker or a user is able to make inserts into this column. Think of this as, for example, credit cards that an attacker or a user can fill in his own credit card, and by doing this, he can later extract the data. So users can make these insert operations, and also they can time the time it takes for the web application or the database to respond to their insert operation. Then the attacker can succeed in stealing all the data from the database. And the complexity of this attack and the success probability of the attack is based on many parameters that I will describe during this talk. But mainly, I can say that it's the number of bits of the sensitive field times the number of values you want to steal, the attacker wants to steal. So more explicitly, this attack depends on the indexing structure used, B-trees, which is used in most commercial databases. However, we only implemented this attack against MySQL, and I'm going to tell you about our MySQL implementation. So what does this vulnerability imply? What can we say about the problem with indexing sensitive data using B-trees? Well, apparently indexing might be a bad idea in terms of security, and it needs to be researched further to understand how big is this issue, and whether a given implementation, a configuration of a database is problematic or not. But there is a trade-off here between efficiency and security, as it always happens. And also, taking into account the complexity estimate I just told you of, this is only one attack. We are not sure if this attack could be improved. and we do have some evidence that it could be improved. So I'm going to tell you about some numbers and some results that we achieved, but probably one could do better. So I mentioned indexing tables is a bad idea, and let me give you an example of why is this so. Imagine a content management system that has users and passwords in a table, and they are displayed in this way in the web application. From the web browser, you can register, and registering, you type your username and your password. Of course, passwords cannot be seen, and they are written as asterisks, hidden from standard users. However, imagine that both username and passwords are sorted, so that when you click on username or you click on password, they are ordered alphabetically. So let's say that when you click on password, they are reordered alphabetically by the password. Then, for example, here you know that Tom's password is earlier in the dictionary, in the alphabet, than Dick's password. And if you're allowed to add username and passwords, many of these, then you can make a divide and conquer attack, a binary search, and find out any of the passwords in this table. So indexing is problematic. Sorting, is problematic. Now, the attack I'm going to present is different from this, but this should be evidence that some people that think that sorting isn't problematic, they are wrong. So to continue this talk, I will go through database management systems and the indexing structures. I'm going to prove or give evidence that these databases leak information, and then build on the attack. So how does it go? Now, database management systems are applications accessed by either web applications, web servers, or any application that has a database in the backend, or by standard users. They have a persistent storage, they have a hard drive typically that stores all the information, and this needs to be stored efficiently for the web server, the web applications, and users to access this information efficiently. So typically they use the relational model or the SQL standard or variations of this. To summarize this, one could say that data is stored in tables. Each row of the table stands for one record, and all the fields of the record are divided in columns. For example, username, password, or here, name, passport, football team. And these rows are sorted by the values somehow in the database. If they weren't, then searching for the data or making insertions would be very inefficient. And also it should be noticed that you cannot have all this data, huge amounts of data in RAM memory. So it must be stored in the hard drive. And typically what one will do is access chunks of this memory and perform operations over these chunks in the RAM memory. So this is the architecture of a typical database management system. As I mentioned, data is sorted in chunks, which are called page disks. And every time a user performs a query, it goes through all the blocks there. But to summarize this, the user will make a query. This query gets compiled, and it is forwarded to the storage engine, and the storage engine will access only the chunks of memory, the pages that are necessary for performing this operation, and retrieve this data to the execution engine and finally to the user. And it should be understood for this talk that the cost of each of these operations is typically dominated by the access to the hard drive, by writing and reading hard drive. So database management systems try to minimize reading and writing in hard drives. However, by doing this, there are time differences between each of these operations, and we thought that perhaps you can use these timing differences to extract information to the database, from the database. Okay, so a little bit about structure of the database and how data is stored in the hard drive. There are many different implementations of this, but in the end, for every sorted column, you pair this column with an identifier for the record, maybe a pointer, maybe the data itself. Here you find two examples, the unclustered index and the clustered index up and below. And this is the way the table on the middle is stored. These columns that are sorted are called search keys, or from a search key you can build one of these columns. And what you need to do is sort efficiently these search keys and have a data structure for inserting these and looking for them efficiently. So one of the ways to do this is with B-trees. A B-tree is an idea that dates from the 70s, and it's basically a balanced tree, meaning that from the root to each leaf there's the same distance, the same length, and there are some design principles which are known, and then different database management systems will implement this differently. For example, each node should be half full, and this rule is almost always obeyed, but the nodes have a full capacity. We will call this the N, the size of each page. And here you see some search keys, 28, 8, 13, 28, 35. And these search keys are paired with the data as I showed in the slide before, like this. These passport numbers stand for the leaves or the values, the search keys in this tree. So here I only put the search key values, but this should be linked to the actual data somehow. Now leaf nodes, the lower nodes, are stored in a linked list somewhere in the hard drive, and you can see how to search for values in here. Now if you want to search for a value, say for 5 in this tree, you start from 28, and then you know that you need to take the left branch, and you get to the node that has 8 and 13, and since 5 is smaller than 8, you go to the left branch again, and you access the node that stores this data. So the way a database management system will work is the search engine will know that it has to access this page, which has the values 1, 4, and 5, and it will send this page to the buffer with all the data accompanying it, so it can be accessed by the user. So inserts are also likewise easy. I'll show you below. The problem is with inserts or deletions that require, for example, deleting or adding one new node. Let's see. Here's some toy examples. Imagine these 2 leaf nodes. I forget about the rest of the tree because it wouldn't fit in the slide. And we will start adding values to these nodes and see what happens. For example, we add 15, and it goes to the left node. And we add 21, it also goes to the left node. 18, 43, and now we add 33. And since it can't fit in this node, and it should be placed in this node because it's a value between 1 and 43, then the node must be split. And it is split in 2 halves that you see printed there, one with the values from 1 to 10, and the